To build the next generation of global infrastructure, we need high-density power and lighter, stronger advanced materials. But at the exact same time, strict climate mandates dictate that we completely stop burning fossil fuels to get them. This creates an immediate problem for coal. Because of its long history as a combustible fuel, it carries immense environmental, social, and governance baggage. It is viewed as a toxic liability. But this view confuses the resource with the method of processing it. The carbon molecule itself is valuable. The actual issue is the act of setting it on fire. If you apply targeted physical forces instead of heat, the amorphous carbon structure organizes into rigid, two-dimensional hexagonal lattices, graphene. Reclassifying coal as a molecular feedstock provides a massive, localized, domestic supply of the critical materials required for next-generation energy storage and defense technologies. By separating the physical carbon molecule from the act of combustion, we eliminate the atmospheric emissions. What remains is a high-yield strategic asset hiding in plain sight. Raw bulk coal is a disorganized, three-dimensional web of carbon atoms. It is messy and amorphous, but it holds intense latent chemical potential. For over a century, our only method for accessing that potential was combustion. Burning destroys the molecular structure to release a short burst of heat while pumping tons of carbon dioxide straight into the atmosphere. Molecular dissection takes a different approach. Using non-equilibrium cracking, applying specific energy frequencies rather than fire, we can break the bonds holding the impurities together, allowing us to extract perfectly ordered two-dimensional carbon lattices intact. Looking at this breakdown, the contrast is stark. On the left, we have raw, unprocessed Appalachian coal. Through this dissection process, it is converted directly into battery-grade graphite and advanced carbon structures on the right. This dissection process proves that coal is the ultimate graphene mine, yielding over 4.5 times the carbon value of natural gas per ton. Because the carbon is extracted and physically locked into solid materials rather than burned, zero carbon dioxide enters the atmosphere. You retain the economic value of the carbon without the environmental damage. If you followed material science over the last decade, you have likely heard immense promises about graphene, and you've probably noticed that very few of those promises have materialized in commercial products. The material was originally discovered by physically peeling layers of graphite apart with adhesive tape. While that method won a Nobel Prize for proving graphene existed, it is practically impossible to scale up for mass industrial production. The main industrial alternative has been chemical vapor deposition, or CVD, which involves growing graphene on a copper substrate. This process requires expensive equipment, specialized environments, and produces very small yields for the cost. More importantly, the CVD process inherently introduces trace metallic and ionic contaminants into the final sheets. For highly sensitive semiconductor and electronic applications, even microscopic contamination renders the graphene useless. Manufacturers clearly want to use graphene for advanced batteries and processors. The bottleneck is the absence of a high-volume, low-cost manufacturing method that preserves the material's absolute purity. To bypass the limits of CVD, engineers developed a physical method, two-stage, wave-based, non-equilibrium molecular cracking. Here is how the physics work. We begin with a pulverized lump of coal, packed with its dense, amorphous internal molecular structure. In stage 1, the flash phase, this pulverized coal is injected directly into a 10,000 degrees Celsius plasma arc. The extreme temperature instantly vaporizes the solid carbon structure. At this heat, the varying elements within the coal separate. All heavy mineral impurities melt and drop out of the vapor cloud entirely, collecting at the bottom as an inert, glass-like slag. This leaves a highly purified carbon vapor. We then move to stage 2. A targeted precision resonance microwave frequency is beamed directly into this remaining cloud. This microwave frequency is meticulously tuned to vibrate and snap the remaining carbon-hydrogen bonds without destroying the carbon itself. Freed from those bonds, the carbon atoms rapidly crystallize into flat, perfectly uniform hexagonal graphene sheets, which fall out of the vapor for collection. Simultaneously, the hydrogen atoms that were snapped off rise to the top of the chamber, generating massive volumes of clean, base-load hydrogen gas as a direct byproduct. Because the original coal carbon is now permanently locked into these solid graphene sheets, it cannot enter the atmosphere. Factoring in the clean hydrogen produced, this specific process achieves up to a 115% net carbon removal rate. By relying on physical wave frequencies rather than chemical catalysts, we eliminate the contamination problem while processing bulk tonnage. This rewrites the unit cost and purity limits of electronics-grade carbon. However, building an entire business model solely on a flagship product like electronics-grade graphene is a massive financial risk for early-stage commercialization. This schematic details the 5-step conversion pipeline, moving from feedstock characterization on the left all the way to advanced manufacturing on the right. Looking at the lower left quadrant, we see that this single pipeline produces multiple tiers of high-value carbon products, depending on exactly where you stop the refinement process. Before reaching pristine graphene, the process outputs activated carbon for water purification and graphitic materials for battery anodes. These are well-established multi-billion-dollar markets with immediate, steady commercial demand. The mineral slag separated out during the initial flash phase contains recoverable concentrations of rare earth elements, gallium and germanium, materials strictly necessary for domestic defense and semiconductor supply chains. This creates a durable economic model. A single raw coal feed is diversified into a broad portfolio of advanced materials, generating immediate revenue from graphite and rare earths, which insulates the operation while the higher-tier graphene market matures. We can already see this commercial transition happening in one of the most heavily industrialized sectors in the world, cement and concrete production. To bind traditional concrete together, producers heat limestone to create clinker. This single industrial step requires so much energy that it accounts for roughly 8 to 10% of all global carbon dioxide emissions. At the microscopic level, concrete is actually quite brittle. When put under mechanical stress, tiny fissures begin to form, eventually leading to structural failure. If you add just a 0.01% mixture of extracted graphene platelets, the material behavior changes entirely. The graphene acts as atomic rebar. It weaves into the concrete gel and physically bridges those microscopic gaps, stopping cracks before they can spread. In field testing, this tiny fraction of graphene reinforcement increases the total compressive strength of the concrete by 34%. Because the material is so much stronger, producers can reduce the volume of heavily polluting clinker by 20%. Proving that graphene adds decisive value to a bulk, low-tech commodity like concrete creates immediate cash flow. This establishes the financial foundation necessary to build the larger facilities required to eventually supply high-tech semiconductor manufacturers. The physics are sound, and the initial markets are proven. The final variable for success is logistical efficiency. In any material refinement operation, the largest single operational expense is almost always transportation, moving millions of tons of heavy raw ore across continents to specialized processing facilities. We can eliminate that cost by deploying modular processing sleds directly to the mine head, dissecting the coal exactly where it is pulled from the earth. This rendering illustrates the 56-acre Opal Advanced Carbon Materials campus in western Pennsylvania, designed exactly for this purpose. It utilizes an existing industrial footprint that already has 5 million tons of surface-accessible coal and active on-site coal seam methane for localized energy. There are no rail delays or ocean freighters required to deliver the feedstock to the reactor. By anchoring the facility on top of the raw resource, the operation insulates itself from the volatility and cost of global supply chains. Historically, advanced materials startups fail because they attempt to raise $50 or $100 million upfront to build a massive commercial facility before they have firmly proven their process at scale. To protect investor capital, this operation uses a strictly gated, milestone-funded progression model. Capital is distributed across 5 distinct stages. The rules of this structure dictate that one stage must be thoroughly validated before a single dollar is committed to the next. It begins with Stage 0. A seed round to independently characterize the specific coal feedstock and confirm the graphene yields in a laboratory setting. Stages 1 and 2 fund a pilot production lab. The objective is generating exact kilogram samples of graphene and activated carbon for defense and industrial customers to test and validate. The final commercial scale raise, for $50 million or more, is contingent on those customers signing binding development and purchase agreements. This stop-loss staging ensures that technical viability is proven before heavy spending begins. Technology risk is completely separated from commercial scaling risk. The timeline of this stage development aligns precisely with the impending growth curve for these materials. This market forecast projects that the combined value of graphene and graphite will accelerate to over $108 billion by the year 2035. That growth is driven by hard industrial demands across solid-state energy storage, high-efficiency semiconductors, and critical aerospace defense systems. We are reaching the realization that coal is a misallocated foundational chemical. By moving away from combustion and toward molecular wave dissection, we stop treating carbon as an exhaust problem. Combined with on-site processing and strict financial de-risking, this framework turns an environmental liability into a secure domestic supply chain for America's technological future.